Section 11.2 talks a lot about conservation of energy and the situations in which that applies. Okay, we want to pay attention to a couple of vocabulary terms, especially the different kinds of collisions. There's a number of different kinds, not just actually those two, and also this term mechanical energy. All right. So we know the law of conservation of energy. I shouldn't have to go through that too much, but it's very similar, of course, to the law of conservation of momentum in that you need a closed and isolated system, and then the thing is conserved. Energy is conserved in this case. But that doesn't mean that all kinds of energy are conserved, right? It means that the total energy is conserved. But remember that energy can change forms quite a bit. So what about the energy that we are most interested in, right? Which is generally in physics, kinetic energy and potential energy, right? Together they make up what we call mechanical energy. You might say even useful energy, right? Because if you're going to do something with energy, you're generally going to be looking at like the kinetic and the potential energy to determine what you can do with it, right? So anyway, mechanical energy is just a combination of those two. So the question might be, really, do we conserve mechanical energy? And that's a lot of what we're going to look at here. I highlighted the word candlepin because I actually had to look this up, what a candlepin bowling ball was. Candlepin just means it's a different form of bowling, that they have skinny cylinders for the pins instead of the ones we're used to, right? Anyway, so when is conservation of mechanical energy a thing, right? When do we have the kinetic and potential energies before equal to the kinetic and potential energies after? Because that's a nice, handy little equation to use, right? Well, there are certain instances where we can expect conservation of mechanical energy, right? If you just drop an object, right, its potential energy at the beginning, we expect generally to be about the same as its kinetic energy at the end of the motion. Also, when something rolls down a ramp, we actually expect it, as long as there's not a lot of friction on the ramp, we expect it to have basically the same kinetic and potential energy at the end of its motion as at the beginning. So you're looking for the absence of things like air resistance and friction. Okay, so if those are generally absent, then mechanical energy can in fact be conserved. However, when something actually comes into contact with something, now things do get very complex, and so you have to watch for that. So like for instance, you drop the ball, it has gravitational potential energy, it ends up with kinetic energy, right? But if that ball doesn't come all the way back up to your hand, right, where you dropped it from, what's going on? Why isn't it just picking back up the potential energy from the kinetic energy it had when it bounced? Well, that's because you've transformed some of that energy, right? Some of the bouncing ball, right, it compressed, and as it compressed, some of that energy turned into thermal energy. Actually, the molecules inside sort of ran into each other and sort of caused friction inside. And so you get thermal energy. Or you get a sound, right? There's vibrations that are occurring, and that's going to cause sound energy to be emitted. So you can have transformations in collisions. All right, but if you look at a few instances where conservation of mechanical energy sort of applies or implies most closely, you might say, roller coasters, right? Downhill skiing, right? A lot of your potential energy turns into your kinetic energy basically by the end of that. Pendulums, right? So you see this transformation. I'll go through this one really quick, right? The bob gets released. It's got potential energy, starts to turn into kinetic, all kinetic by the bottom, and then goes back into potential energy. Okay. Pay attention, by the way, to this problem-solving strategies section here. It makes a big deal out of identifying your system, and this really is a big deal. Okay, you need to make sure that your system is both closed and, very importantly, isolated, right? Otherwise, there's no way you can use this convenient little Ke plus Pe equation that we have here on the right. But if you do have an isolated system and you only really have potential and kinetic energy being a really important factor in it, then that equation, like I said, it can be used and it's very helpful. All right, last thing in this is about the different kinds of collisions. Now, we already know that momentum is conserved in collisions, right? Great. But what about energy? Well, it turns out that it depends on the kind of collision, right? There are collisions where energy is conserved. Those are called elastic collisions. So this would be like two pool balls running into each other, right? And one of them hits the other and the second one takes on the energy of the first, right? And we're kind of familiar with that. We've seen that in the last chapter. That's an elastic collision. However, if two things hit and stick together, they are going to lose some kinetic energy. That is a given. It will definitely lose kinetic energy. You can do the math to check it, but we call that a perfectly inelastic collision. If they don't stick together, but you still lose some energy, right? There might be some sound given off. There might be all kinds of other things, some thermal energy, right? That's just called an inelastic collision. So notice that the kinetic energy after the collision is less than the kinetic energy before. And then finally, there's actually what we call superelastic collisions. This is a little bit rarer, but let's say two things hit each other and they, explode or something, right? Well, there's going to be more kinetic energy suddenly that is going to be produced. So you have to have energy coming from some other situation to add that in. Okay. Now, what kinds of things are going to undergo elastic or inelastic collisions? Well, harder objects are generally going to do nearly elastic collisions. Okay, again, think pool balls, right? Inelastic collisions generally are going to be softer things, right? The softer they are, generally, the closer they get to a perfectly inelastic collision, right? Because they're going to stick together a bit more. All right? So those are different kinds of collisions. The rest of this chapter is examples. Please go through those and check your